Right, good afternoon everyone. It's 12:02, yes. So today we're going to model our pendulums because we need to be able to estimate the maximum angle from the motion of the pendulum with a single sensor at the bottom. So we've got this sensor, a light beam sensor that crosses the path of the pendulum right at the bottom of the swing where the pendulum is actually moving at its fastest speed. So we need to work with that information in order to then model the motion in terms of the maximum angle theta that the pendulum swings. So we're going to do this with a very simple model based on simple harmonic motion, which is an approximation for a pendulum. You can improve that by looking at the energy analysis of the pendulum because it has zero kinetic energy at the top of its arc, and when it reaches the bottom it converts that potential energy into kinetic energy. But we can do that a little bit simpler in terms of the outcomes just by modelling the forces on the pendulum. So this is basic physics. Hopefully you'll remember how this all works from your physics in undergraduate years. So we have a force which is due to gravity, which is the mass of the pendulum multiplied by acceleration due to gravity, g. So what we're doing here actually is an important assumption. We're modelling the pendulum as a point mass. So that mass m shown here as a point mass is really the centre of gravity of the pendulum itself. So we can then simplify the analysis just by considering that point mass, and we'll look at that assumption at the end. So therefore we have this mass, we can then model a gravitational force, and we can divide that up into two orthogonal components. One in the direction of motion, which is this guy here, mg sine theta, where theta is the angle of the pendulum from the bottom position. All right, so you get similar triangles here, so you can then decompose this into the two components. The component, obviously in line with the pivot point, is cancelled by a force in the pivot point, and we don't have to worry about that component, so we're just left with the perpendicular component mg sine theta. So therefore the acceleration of that mass is minus g sine theta, and we can approximate that in practice by minus g theta, where theta is small. Alright, so for our purposes, small's less than 20 degrees, thereabouts, typically, and the errors will be quite small in that regard. We can actually work that out later on. So we can then model this acceleration by looking at the... Right, so this is... The position is r times theta, so we can look at the second derivative of r times theta. So that's d squared theta by dt squared multiplied by r. R is a constant, so it comes out. So you can then work that out as minus g theta. Okay, multiplied by r. Sorry, the r is already included in the position, so that is correct. So we end up with a second order differential equation on theta, which is minus g on r theta. All right, you should recognise that form as simple harmonic motion. It's a basic equation that you will have seen when you talk about feedback systems and second order systems. So we know the solution to that equation. It's a trigonometric relationship. All right, so we can actually write down the solution in the form of a sinusoid, which is theta max, which is what we're interested in, sine of some angular frequency omega multiplied by time plus some phase angle. So we don't really know omega at this stage, we don't know the phase angle, and we don't know theta max, but we can work with the equation to derive these things, and we can include measurements from the pendulum system. So if we take the first derivative of that, then it's just omega theta max. Pen stop working. Times cosine of omega t plus phi, where omega is 2 pi radians per period t. So that's standard format that you would have seen in other signal processing and communication systems. All right, so the second derivative now is omega squared theta max multiplied by minus sine theta omega t plus phi. All right, so we now can substitute that in, and we can substitute that in this equation here, equation 1, and we can relate that to G and R. All right, so let's do that. So we've got this expression here, and you get minus omega squared theta max, and you have sine on both sides here, minus G on R theta max sine of omega t plus phi. So those sine terms we can eliminate, and we're left with an equation relating omega squared theta max and G and R. So theta max disappears. So therefore, minus sign goes away, so we get omega squared is G on R. All right, so that's nice. We can relate that to our period. So we've got the square root of G on R, and if you substitute your 2 pi on t, you can then work through So we're interested in the period of this motion, and that's square root of G on R. So solving for t there, might as well do that, is so we're going to square both sides, and it's G on R. So we get okay, so what I'm interested in actually is R. So R is G t squared on 4 pi squared. Right, so that's all very good. So what we'd like to do now is work out theta max, in fact. So we've got some basic equations here which I can label, and we can work with those. All right, so one way to address this is we know the equation of motion for the speed, the angular speed. So theta dot is related directly to omega theta max cos omega t. So how can we then use that information? All right, so we need to then consider the maximum speed of the pendulum, and that's what you can measure, you see. At the bottom of the pendulum swings past, it's going at maximum speed. Okay, so let's work that out. So what is the maximum speed of the pendulum? Given once we measure that, we can then relate it back to our parameters, one of which is theta max. Okay, so let's have a look. So we've got theta dot, the derivative of the angle is equal to omega theta max times cosine now of omega t plus phi. So from that you can see immediately that the maximum angular speed maximum angular speed, so we call that theta max. Theta dot max, okay, is then equal to omega theta max. Because the cosine maximum is 1, we know that occurs at the bottom of the swing, so that derives our theta max dot. All right, so that's the maximum angular speed of the pendulum, and it's related to the maximum swing angle. Very nice. So, one way to solve this is we can measure the period. So let's resolve this in terms of our omega. It's 2 pi on t. T is the period of the pendulum. Very easy to measure the period as well. So we're converging on a solution here. And what we need to do now is somehow measure theta dot max. All right, so what we're going to do here is take a first stab at this formulation. So I'm going to suggest that we can use theta dot max as equal to the maximum speed of the pendulum divided by r, where r is the radius to the point mass. Okay, so if you divide by r, you'll get the angular speed. We know the maximum speed, so you divide by r, and that gives you theta dot max. All right, so we can now substitute that in this equation here, which is 4. So we are measuring the maximum speed. Hopefully we can then derive theta max is equal to t times theta dot max multiplied divided by 2 pi. Okay. So just substituting that maximum speed divided by the radius and 2 pi. So that's our first attempt. And I'll call this equation 5. Right. So, can anyone spot a big problem with equation 5? It's actually incorrect. I love giving you incorrect information because that's what you'll end up with if you don't think about the problem. And most students come up with this solution, and it's actually wrong. So that's why I've done all this, to make the point that it is actually wrong. So why is it wrong? Well, it's not actually wrong, it's just not useful to you. All right, so let's take this further. The point about it is r. How do we know r? Well, we can go back to our previous equation number 3. Substitute r in. Okay, so let's do that. So we get 2 on 2 pi, and 1 over r is 4 pi squared on gt squared. Times max speed, and I think that's good. Yep, gt squared of 4 pi squared. So we can then simplify that, and that's removes 2 pi gt max speed. Okay, so that's our theta max equation. All right, so this is what most students will report. They'll go to the lab, they'll measure the maximum speed, they then divide by the period, and 2 pi and g you can calculate pretty easy. That gives you theta max. However, what they found in practice is as the period changes, so you move the mass up and down, instead of theta max decreasing when the period increases, it turned out the other way. It turned out that the theta max increased in practice when t increased. So this is wrong, actually. This equation is wrong. All right, has anyone worked out why it's wrong? Or what's the problem with this equation? Can anyone tell me how you measure max speed? This is the critical element here. How would you measure the max speed? It's not a trick question, it's straightforward. How would you do that? No, I'm just talking about in the lab. You're designing the equipment, you've got the measurements. Well, how do you process the measurements that you're making to calculate max speed? So you're measuring the crossing time, transition times at the bottom of the pendulum with the mask. All right, so how do you derive the max speed from those measurements? Yes?
We use the parallel oscillator and use this distance to divide the parallel.
So when you say period, do you mean the time between swings at the bottom, or do you mean the time it takes for the mask to cross through the beam?
We have the distance, the length of the mask.
Yes, the length of the mask, yes,
The parallel.
and the time between the transitions across that mask. Yep, that's good. That's how you do it. Correct. Is that the max speed you're actually talking about here? That's the question. And the answer is no. All right, so why is it no? All right, well, let's go back to square one.
Slow down once it reaches like the middle. When it
No, it's actually the maximum speed occurs at the very bottom because the potential energy is all converted to kinetic energy, and that's going to be the maximum. We know this. Ignoring friction for the moment, but even with friction it'd still be the maximum. So let's go back to the assumptions that we made at the beginning, which is right back here. So the assumption is we have a point mass and we're measuring the radius to that point mass, and we're calculating the speed based on that radius. Okay. So, as you know, you can move the mass on the pendulum up and down and change that point mass position, can't you? So can anyone now tell me what the issue is? Yes, so it's a different height, yes. So what's the solution? So we would like to measure the maximum speed at this point here, but the pendulum's actually moving across a bit lower on. So the mask will be much lower than the point mass or the centre of mass position of the pivot arm, okay? So we're not actually measuring the maximum speed where we said, we're actually measuring at a different position. All right, so let's go back and do this properly. All right, so we can still work with this equation here. This one's good. So let's have a look at theta max dot. Theta dot, the maximum angular speed of the pendulum. Okay, we need to measure that. And we can measure that by looking at the speed of the bottom of the pendulum as it crosses the light beam sensor. So let's draw another picture here. This is our mask. Here is our centre of mass R to this point here. And we're going to denote the length of the pendulum L, which is different from R. L is not equal to R, obviously. So therefore, theta dot max will be equal to the maximum mask speed, I'll say, just to differentiate that, divided by L. And you can measure L physically, just get out your tape measure. There it is. And now we can substitute that in. I'll call this guy VL. So that's now VL on L, and therefore theta max without the dot, which is what we're interested in, is T times VL on L, all divided by 2 pi. All right, so this is good news because we can now be guaranteed this is correct. And I'd like you to compare this now with this expression here, particularly the position of the t in this expression. You see t is now on the numerator, not the denominator, just as I talked about earlier. So theta max is actually proportional to the period of oscillation of the pendulum. T is the time from crossing that way back and then crossing again, the time for a complete period of the pendulum. And VL is a measurable quantity. It's different from max speed up here. L, 2 pi are obviously constants, so you can see the maximum angle is proportional to the period, not inversely proportional. So yeah, this guy caused problems when the masses moved up and down, and people got that wrong and they did all sorts of things to try and fix it, but the problem lay in the maths behind the derivation. So I've helped you guys out. I've solved a problem for you that you probably didn't know existed, but nevertheless that will speed up your implementation. Any questions on that? Yeah. Alright, so what we're trying to do here is just to get you progressing with this project. It's really about real-time systems, not really about system modelling, so we just want you to get the modelling correct without wasting a lot of time. Okay, what I'd like to do now is just move on to our real-time systems software tutorial problem. This one is just taking one step further with our synchronization function. Now, the reason behind looking at these problems is when you're writing your code in terms of multiple tasks, in terms of the Pendulum project and other real-time systems, you need to be mindful of issues that arise when you write functions that have to be re-entrant. This is an example of that. And how to coordinate multiple tasks in a real-time system that becomes more complex as you add tasks. All right, so here we have this synchronization problem. We have now numproc as a constant. We know that a priori it might be 10 tasks. We know that before we start. We'd like all of these 10 tasks to synchronize using one system function called sync. So the first 9 tasks to call this function should wait for the 10th. Once the 10th arrives, we all proceed on together happily in synchronization. That's the objective here. All right, so let's have a look at how we might solve this problem. And I'm going to get you to have some thoughts on this as we go through. All right, so the first thing is, what information do we have to keep track of internally within the sync function? So this sync function, yes, it's reused by multiple tasks. We're going to come back to that point later. But internally, we'd like to keep track of memorize, if you like, store some information. So what do you think that information is? Now, just to prompt you a little bit, if you look at the previous solution that we looked at, where we had a single function, this guy here, with just 2 processes now, we're generalizing beyond 2. We stored this static Boolean variable called first inside the function. Static means it lives in its storage beyond the calls of the function, but it's only visible within the function. So what can we do in this case that's similar to that? What do we need to store in terms of working out what to do within the function? So I would like you to tell me a internal variable that we need to keep track of. What is it? So what information, just imagine you are sitting inside this function and you're trying to work out what to do when some new task comes along, calls you. What information do you need in order to work out what to do? The choices are you block the current caller or you release everyone that's been called previously. That's what we're trying to do with synchronization. So just have a guess. Sorry? You have to block the caller if the caller is what? You don't block every caller. That's the point. Priority is not relevant here. We want to block 9 callers and let 1 guy through. How do we do that? Yeah, you're on the right track. It's like a queue, but it's simpler than a queue, actually. A stack. All right, so if I gave you the job to do this and there's 10 people around you and they come up to you, okay, and they say, sync me, please. What do you have to remember? You don't remember their faces. I'm not really interested in that. The number, yeah. How many guys have you already seen? All right, that's the key, isn't it? So that's how we try and solve these problems. So what sort of variable am I going to stick in here? What's the type? Int, yes, good. We're making progress. So I would say we call this the number arrived. And being a static variable, you really have to initialize that here. So when we first start, well, there's obviously no one arrived, so that's easy, it's 0. Okay. Now, what do we do when we call sync to this number arrive? Sorry? Increment it, yes. So let's increment num arrive. So now we do have an up-to-date count, and now we can work out whether to block or let through the caller. So what condition do you have to check in order to say I'm going to block the current caller? What do you check? It's obviously an if statement. So we're going to do this if something or other, then we're going to wait on our semaphore like we have previously. Yes? So, yep, you want to check the number of arrivals. And numproc is what we want to check it against. Running out of space here. All right, so what are we actually checking? What's the missing character? No. Now, if it's equal to 10, we want to let the guy through, but we're talking about blocking here.
If it's less, if number of arrives is less than
Yeah, good. Okay, less. All right. All right, so that's good, isn't it? And we're nearly finished. So if that's not true, then we're up to number 10 or whatever it is. If numproc's 20, it's 20. What do we do if that's not true? Let's move that up a bit. Well, we're going to do a few things here. So let's put a little bit of space in here. So what do you have to do? Sorry? We've got to do something before we release other tasks. We want to keep our bookkeeping up to date. All right, so what does that involve? So we need to keep this static variable up to date so the next call will be correct. So what do we do to that? We're going to update num arrived to be what? 0, yeah, great. Okay, so we're now ready for the next round of synchronization. And you need to do that first because once we unblock things, then there's going to be new callers coming into this function from unblocked tasks, potentially at any time. So we're going to do this first. So we're actually prepared and ready to handle the next wave of requests. All right, so how are we going to unblock the poor old souls that got blocked on waiting on the semaphore? How do we unblock them all? All right, there's not just one here, there's 9 of these souls lost in space, blocked on a semaphore, sitting there doing nothing. They can't help themselves, they're helpless. How do we help them out? 4. Oh, yep, I like the sound of this. All right, 4, let's call it I equals 0 to what? Numproc -1 actually. So we've got to do 9 what? What are we going to do 9 times? Signal, that's right. Signal on the semaphore. All right, so that's wonderful because now we're going to unblock all of these 9 other people that arrived before us, and we then proceed, we signal them all, and then we return. Looks marvellous, doesn't it? Right. Okay, is this function re-entrant? So it seems to do the right thing, but will it survive the test of concurrency? In other words, multiple tasks coming in here and switching at arbitrary times between any 2 instructions, or this is actually machine level instructions. So even at the level we could split this increment, for example, in half. You might read from memory, increment a register, right back to memory. In between any of those instructions you can get a context switch because we've got a preemptive operating system. Can happen at any time due to an interrupt, bang, we get a context switch. So what do we have to worry about here? Right.
You have to use like meter exclusions.
Yeah, we need a mutex. So we're going to define a mutual exclusion semaphore, create a semaphore with an initial value of 1. And our semaphore that we've just used would be 0. Yep, correct. All right, so let's now work with our mutex. So what are we protecting? Just make that nice and explicit so you understand the problem.
It's between static incline and increment.
So this code, this is not any code, that's just declaring a variable. It's not part of the code, it's just allocating memory. All right? So we don't have to worry about that line. So where will we do it?
Before the increment.
Yeah, okay, before the increment. Okay, so we've got to wait on our mutex semaphore here. All right, so that's protecting num arrive because we could get a context switch here, for example. And that's going to spoil everything. Or even before that. So anyway, we're going to make sure no 2 tasks can read num arrive at the same time and play around with it, increment it, read it, choose if statements based on it. It's all must be consistent. All right, so the next thing is where do we actually signal on the mutex? down here. All right. Why don't we do it here? Couldn't we do it a bit before that? All right, so it doesn't actually matter particularly, but we'll put it here because you told me to. All right, I like that. So we're going to do a signal mutex. Sorry, my writing's here, and of course that's not enough, as we saw earlier. There's another place we need to worry about this as well. Yeah, we've got two cases. There's an if statement, so we've got two branches in the code. We need to consider both branches to couple our wait and signal operations. They have to come in pairs for all paths through the code. So where do we put the other one? We've got two choices. We can put it here, here, or you could have actually put it down here as well before we return from the function. But let's ignore that one. So you have to choose, do you put it before or after the wait here? And we're going to have to put another curly bracket in here to account for adding an extra statement. Right, so if we put it in after the wait, what's the problem with that? We had this problem before, so you should understand this.
Because it's waiting now, so it cannot actually signal the mutex.
Yeah, it's blocked. It can't then signal the semaphore. You get a deadlock situation arise. So the first caller will actually block everything else, and you can't access the critical section beyond the wait because the first guy's holding that semaphore. No good. Okay, so we must do it before the wait. So you'd have to put it in here. So the mutex needs to be signalled here. And so that looks pretty good, actually. All right, so who thinks this is a great solution? You do. Oh, that's good. But everyone else that suggested things doesn't agree with you. I wonder why. All right. Okay, so this is actually not a good solution, unfortunately. There is a fundamental problem here, but I'm going to leave that for you guys to work out during the week, and we'll talk about it next week. Because that's what happens in reality. You get a problem. So when you run this, there's going to be an issue where the synchronization fails under some conditions. And it's a very odd thing, but it does happen every now and then, and you'll be perplexed when you run it. You'll think, why is this not working? I went through all the process, I did the proper critical section, and it's now re-entrant, yep, but there's a problem here in terms of the synchronization. So what I want you to do is imagine scenarios where different orderings of arrivals occur, different priorities, and try and work out what can go wrong here, just as a puzzle during the week. And next week we'll discuss this further and look at how to solve the problem that you have detected. And what you can do, which I'll show you next week, is you can work on a method for testing these programs where you insert arbitrary delays between every pair of instructions in the code. And then you simulate it for all possible scenarios. So you use random number generators actually to try and exercise the context switch random positions. And if you were to do that, you would discover a problem. And I'll show you the code that I've used to test these things myself. But I'd like you to think about it. I mean, we're here to learn, not just to look at solutions. I want you to work out how you would approach this problem. Okay. So we'll come back to that one. So let's just briefly introduce fixed point arithmetic. We need this in the Pendulum lab, actually, because we have to run this code for the PID feedback loop, which we'll talk about later, the proportional integral differential gain feedback loop for the control of the motor has to run really fast in order to keep up with the servo rate that we're looking at. So we need to avoid floating point arithmetic, and it's much faster to run fixed point integer arithmetic as a basis for real-time design. So often you'll find this topic comes up. And there are some intricacies around this, particularly with regard to rounding. So if you want your arithmetic to be as accurate as possible within the precision number of bits, you need to think about rounding. So we're going to look at different representations where we put the binary point, as it's called. It's like a decimal point, but in binary. And see how that is implemented in addition, multiplication, and division. And then look at rounding issues regarding that. All right, so floating point, yes, it exists, but in hardware it may not be supported by your processor because it might be a low-end processor that, sure, it runs fast, but it doesn't have that extra cost of floating point coprocessor. So we can actually run, if you were doing this in hardware directly, you can run fixed point arithmetic extremely fast compared to floating point. So there's big performance advantages. And in C programming, you know you can do integer arithmetic very easily with these operators. You can use addition, subtraction, multiplication, division, and shifting left and right. Shifting right and left. That's the right, this is the left. So division is a special case. It's integer division. You don't have a remainder available in C programming, although in hardware, of course, you would have that available if you wanted it. All right, so the division is not something that you're probably accustomed to, so we'll need to discuss that in a little more detail. But the basic representation is you have integer bits, so there might be, say, 10 bits, and you might have, say, F fractional bits, might be 6 fractional bits. So 10.6, that's 10 integers, so you can go up to 1023, and you can have fractional bits of effectively 1/64th of a unit in your system of arithmetic. All right, so that's quite common, and you can change the position of that in your code. You're just defining what you mean by that integer. So you're really looking at an integer variable, but you're just saying the bottom F bits are representing a fraction of a unit in some power of 2, negative power of 2. All right, so this 2 to the minus F then becomes your unit of measure of that variable as an integer variable. That's a really good way of thinking about this, because people often get confused. They say, well, you're using integer arithmetic, but you've got rational numbers here, so how does that work? Well, it's just changing the unit system in terms of the F fractional bits. So we can use 2's complement, which is the sign representation commonly used, or unsigned. And with multiplication, you need to be mindful and careful about how that works, because you get different results. Pretty much in addition, there's no drama with using those 2 representations. So let's look at a simple example just to get this concrete. So if I asked you to write down 10.78 in 8.8 format, could you do that? How would you do it? Well, hopefully you can all do the 10. All right, so 10, you know, in binary is 1010, and we've got 8 bits, so we'd add 4 zeros at the start. Okay, so that's where we're going to put our binary point. And what about the 0.78? What are you going to do with that? Now, you can't just convert 78 into binary. That's actually incorrect, because if you think about it, the units of the 78 are 100th, and a 100th in binary does not actually work. It's actually an approximation we'll have to use here, because you have this recurring binary result. It's an infinite progression, basically, to approximate, say, 1/5. because 5 does not divide into a power of 2 exactly, okay? So how would you calculate 0.78 in this situation? Is it really that hard? Has no one done this?
I just know that actually those bytes on the right side are like in powers.
Yeah, they're negative powers of 2.
Yeah.
So the first digit here is 2 to the minus 1, and then the next digit's weighted 2 to the minus 2, and so on. So that's a bit of a clue how to do this. So the technique I'm going to show you is really simple. We just multiply by 2 and then take the integer part and then subtract that and do it again. So that just shifts it, if you like, to the left 1 bit. So here it is. So what we do is we take 0.78 multiplied by 2, so that's like a shift to the left in binary, and we pull out the 1 here because that's the result of doing that, and that's the integer part now of shifting 1 bit to the right with a decimal point. All right, so the other way of looking at that is if we multiply by 2, we now have basic units of a half, 2 to the minus 1, and we've got one of those with some fractional bit left over that can be accommodated by the next stage. So anyway, the result is we get a 1 there from this one here, and we do it all again. Now we remove that 1, so we have 0.56 multiplied by 2, and you get the next digit. You keep doing that, and you end up with this result. The bad news is once you've got down to the end, so we subtracted that 1, but there's still this 0.28 unaccounted for. All right, so that's like the remainder after division by 100. 78 divided by 100, you can't do it perfectly in binary. All right, so that is an approximation. So there's some bits missing here. This could go on forever in terms of the number of bits. All right, so what is 10.78 in 8.8 plus the number 3.75, where we represent 3.75 in 4.4 format? So you're asked to add two numbers here. However, they're in different formats. 8.8 and 4.4 different format. How do you accommodate that change? So this is a very common problem because you've got this representation and you're combining them. How do you add them together?
You use the same reference and you match them. Like, you have the reference point, you match them and you...
Yeah. You have to match the positions of the binary point. So the way we do that is we change... Okay, so we look at 3.75, here it is, in 8.8 format. 4.4 format. So in 8.8 we can pad that out. So you're adding zeros both ends there. So we're talking about 3.75 here, all right? So in 4.4 format it's really easy because you've got 3/4, so that's the 3 and 3, and you need to convert that format into the higher order one to match the decimal point, and then we take this result here in here and we add them together. So once you align the positions, it's just a straight addition. No big drama. So if you did this, you'd end up with this result here, 14.527, and the real value that we're after is 5.3. So you can see there is a significant error in that result due to the fact that we had an approximation where we didn't actually account for that final fraction of the lower order bit in the 8.8. All right, so there are some of the issues that we'll come up against. So yeah, you must remember binary is an approximation when we're doing this stuff. We'll look at multiplication next time. We've run out of time today, but I would like you to look at that problem during the week. Just think about it for 10 minutes a day and see if you can come up with a fault and how to fix the fault. That's what we would like to do. All right, thank you for your time. Put a stop. Yes.